So now let's actually start understanding how to build a simple stereo system. Let's take our coordinate axes. Here I just put a simple left camera here. I'm going to put them at coordinate axes points 0, 0, 0, which is here. Now let's imagine I can basically translate this viewpoint by amount tx just in the x-axis, no change in y, to another location here. So now I have another camera which is located just tx in x direction farther from where the original one was at 0, 0. So both the cameras are exactly the same. They're just now translated by a certain distance. And I have, of course, a new camera which has its own coordinate axes. So right camera is simply just looking at the same view, just translated by x along the x directions. Everything else is the same. In this case, the focal length is the same, orientation is the same, everything is the same. Let's look at this scene from the top, just looking at the xz plane. So here again, I have a left camera. Here now I've actually listed the focal length. Right camera, again, we know the focal length here. So of course, the two cameras are translated by distance tx along x-axis. Tx is also known as the baseline. We have a point, x, y, z. Of course, that point appears in this viewpoint here. We'll call this XL for the left image, the location just in x-axis. We're looking down in x, y is pointing outwards. We're not looking any changes in y in this one. Similarly, that point appears as XR on this viewpoint here. The question now, of course, is if I know XL and XR, can I compute Z, which would be basically the depth of this point here, right? Now, this is where actually we can bring back simple geometry to help us. So let's look at this again back into our 3D simple stereo system. I have a point in 3D. That ray of light goes from this camera, goes through this image and hits that. And another one across just like we saw in the previous example. And of course, that's XL. And there would be an X right here for this one. Same kind of setup as before. Now, we can actually compute using the same equations we looked at the beginning of this lecture that XL basically would be Fx over z, and YL would be Fy over z, right? That's for this point here. And in this case, of course, you can also do the y. In this case, of course, YL is the same as YR. The same point in the right camera, XR is different and XL is not. So here is one thing we can start doing. Basically, we know that this camera is moved by a distance tx. Well, that suggests something to us we can actually use. That basically, if I was to move this point here by that same amount, nothing else is changing, the same point would appear. So in essence, the converse of me moving the camera by distance dx is me moving this point in the other direction, minus dx, and actually taking another picture. So now we're basically saying is rather than taking two pictures by moving the camera by distance dx, I'm just moving the point, minus dx, in the opposite direction and taking another picture. So basically that means is now I have a point T, a point here that should be visible in this one. So we don't have to look at this camera. And of course, now this ray is coming in this way, implying that XR is actually moved there, same translation as minus Tx. So now I can basically compute XR, again F, X is now just this location X here, minus Dx in X direction, divided by z. So that's basically becomes my XR. YR is the same. We haven't changed anything in y. So basically this starts giving me a very interesting way of computing both XL and XR, which are now different just by the top numerator.